Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's a pleasure for me to introduce Richard Hartley once more. He's a frequent visitor to our group. Richard is a professor at the Department of Information Engineering at Australian National University. Richard is world famous for his work on geometric techniques in computer vision, and he's a co-author of a wildly successful book on multiple view geometry in computer vision. That book has proven to be useful in more ways than one. I'll let Richard talk about his talk.
I think Singbing's actually referring to the fact that it's been very useful in lots of people's research, like for propping up cameras and as a book weight and things, your paperweight and things like that. But in any case, I'm going to talk about some work recently that well, I just added 3 or 4 people to this list of joint work this morning when I started adding new things. So, if you want, join the bandwagon of proving optimal methods for solving geometric problems, which has been a topic that I've been interested in for the last while. I should say, maybe some of you here, maybe not, looking around the audience, have heard me talk about this general topic before, but I think that although I might start with some common stuff which is a bit old, somewhat tutorial, at least to a degree, at the end there'll be some stuff which I haven't talked about before, really. Now, one of the things I'm going to pepper this talk with quotes from 2 of my favorite mathematicians. G.H. Hardy, who's a mathematician from, I say Oxbridge, which means he taught both at Cambridge and Oxford at various times in his career, wrote a thing called A Mathematician's Apology. Obviously, he felt he had something to apologize for. We'll see that later. And J.L. Littlewood, who was collaborated with him. I like Littlewood in particular because he said, if I don't work over the weekend, I'll get a good idea on Monday. And if I do not work on Monday, I'll get an even better idea on Tuesday. And I suppose, if you take mathematical induction into account here, then you don't ever work at all, which is quite a good idea. Mathematics is a dangerous profession. An appreciable proportion of us goes mad. Well, I won't try and demonstrate that. Right. Well, convex optimization is a thing which I've been interested in, and I'm just going to briefly sort of say what that is about. Probably these definitions are ones which you're all familiar with. A set is convex. This is a set in Rn. Convex of a line joining 2 points lies inside D. So this is a domain. This set here is not convex because you join x0 to x1, the line goes outside of the set. So that's not convex. The one on the left is. One of the interesting and useful things is the intersection of convex sets is convex. What about a convex function? That's one of the main sort of topics we're talking about. A domain in Rn, let that be called D, and a convex function is one that satisfies this equation here, which is a little bit complicated looking, but all it really means is if you take the graph of the function and join 2 points on the graph, that line always lies above the graph. So it cups downward. That is a convex function. And so convex optimization is involved with the problem of finding the minimum of a convex function over a convex set. And the nice thing is that a convex function always has a single minimum on a convex set. So other properties, convex function is continuous, has a single minimum, as I said, which is good. Sum of convex functions is also convex. So here we are. This is a convex set. The function looks sort of convex, and there's a minimum, and there's always only one. That's a fairly trivial property which you can easily verify. Constrained minimization, then. The problem is, given a convex function and a convex closed bounded region, D in Rn, minimize the function on that region. That is the archetypal convex minimization problem. There's a single minimum, and generally speaking, you can solve this problem. Okay? Though, exactly how the domain and the function specified might impact that, but generally, for all practical purposes, you can solve this problem with fairly standard known techniques. Now, unfortunately, most problems are not convex. In particular, the problems that I'm interested in, geometric vision problems, are just not convex. However, a number of them are what is known as quasi-convex. So what is a quasi-convex? Quasi-convex is a bit different. It's if you take the graph and you say, where does that graph dip down below a certain level, any level, alpha? So the set of points x, such that g of x is less than alpha, that is a convex set. If that is the case, you call the function quasi-convex. So this function here is quasi-convex because wherever I cut it, it only goes down in an interval, right? And that is a convex set. So that function is called quasi-convex. Now the nice thing is that a quasi-convex also has a single minimum on a convex domain. So just a few examples. Here it is, delta, the set where it goes below, the function goes below delta is a convex set. This one, if you take delta, set of points where it goes below delta, no longer is a convex set. If I try and, that's a union of two intervals. That's not convex because I take a line from there to there, it goes outside the set. So this is a non-quasi-convex set. So they're bad news and we try to avoid them. In 2D, it sort of looks a bit more like this. Here we've got, here's a nice quasi-convex function here. Take wherever you put that level, where the function goes below that is a nice convex set. In this particular case it isn't. This is meant to be drawn with a little indentation there. There's a slit or an indentation in the function. That is not a quasi-convex function. Same thing as before. That's quasi-convex, that's not. This is quasi-convex, that's not. All right? So, what is the quasi-convex optimization problem? Minimize fx subject to x is in some convex domain. Once again, where f is now quasi-convex. And this type of optimization problem is solvable. And we'll see a bit about how you might solve that in a bit. The maximum of quasi-convex function. This is whereas the sum of convex functions was convex, the sum of quasi-convex functions is not quasi-convex. And I was going to, just briefly. Doesn't matter. Oh, there it is. Yes. Okay. I should have a slide for this. But if you take a quasi-convex function which looks like this, another one which looks like this, and add them, you get something which does that. Well, that, if you can't see down here, not quasi-convex. So you cannot sum quasi-convex functions and get a quasi-convex function. And that is unfortunate because that's the whole problem behind the difficulty in solving these geometric problems. But the nice fact is that if you take the maximum of a set of quasi-convex functions, that is quasi-convex and has a single minimum. So therefore, if I take all these functions, each is quasi-convex, and I take sort of like the upper envelope, take that function, that then is quasi-convex and has a single minimum. So now, the minimax, this leads you to be able to solve this type of problem, the minimax optimization problem. Find the minimum over all x of the maximum of a set of functions. So think of these functions fi as being measurements which depend on a value x, right? And they're error estimates, right? So I want to minimize the error. So in the usual way, you'd sort of square the errors and find the sum of the squares error. But if each of these is quasi-convex, their sum is not. So I can't take the sum of squares and hope to be able to find the minimum. But I can take the maximum of these, and that will have a single minimum. So we'll see that again. So what it leads us to be doing is solving minimax problems rather than sum of squares problems, otherwise known as L infinity norm. So it can be written in a different way where you're minimizing S such that fi of x is less than S. How small can you get all these functions, all these residuals? Right, so one of the ways, here's a problem called the triangulation problem. And the idea is find where all these rays meet in space. Of course they don't, so I want to find a point somewhere in here which is closest to where they all meet. In other words, take a point there, project it back. These are supposed to represent images, and this is a projection center. Project them back into these images and minimize. Now typically you minimize the sum of squares errors in these sort of geometric problems. I'm saying minimize the maximum error and then we can solve it. So the idea is, okay, if the error is a certain value delta, the point must lie in a cone. If I sort of say, here's the size of the error, all the points which project to a point close to my image point must lie in a cone, like this. Clear enough? And if I do that with all of those, I say, okay, so what these are supposed to represent are cones from the projection point through a little circle in the image plane that projects to a cone. Right? Now, I make that cone, that little circle, a given fixed size, and I say, is there a point in space which maps inside that error circle in all the images? Now, that's the same as saying, if I back project the cones, do the cones intersect? Because if they do, I can take any point in that intersection of cones and project close to the point. Right? So, how do you solve that? Well, you do this with a process known as second-order cone program, which will actually tell you if there is a point which lies simultaneously in a set of cones. This is a convex optimization problem. Given a set of cones, is there a point which contains them? That is solvable. So what you do is you sort of say, let's set the size of the cones. Do they intersect? Well, yes, they do. Therefore, I can do better than this. So I do a little bit. I make the cones a bit smaller, and I say, do they still intersect? And, well, yes, they do. So then I try a little bit more, and I say, well, they don't intersect now. So that means I've gone too far. There's no point which will map to a point sufficiently close in all these images. So then by a process of bisection, I ultimately find the optimal error and hence the solution, which is the point in space where they all meet. Okay, so just as relief from mathematics, Littlewood said, I sort of like it, the first test of potential in mathematics is whether you can get anything out of geometry. Well, I particularly like geometry, so let's have a look at a few geometric problems that can be solved in this general way. And I'm really sort of going back over past work just to give you the idea of what can be done here. So the triangulation problem is, as I said, given a set of known, this is the same problem as I just discussed, given a set of known image points projected from various camera centers, where is the point in space which is the best approximation of a point which maps to all those? That's the triangulation problem. And you can solve it by that process of second-order cone programming and bisection. Now, there's no exact solution unless the rays meet exactly in space. You require a solution that minimizes the back projection error. Now, the exact solution for this problem in two views, just two views, non-trivial problem really, but it was solved in 1995 by me and Peter Sturm. It actually involves the solution of a degree 6 polynomial. But what about three? Well, furthermore, there do exist local minima to this problem if you're trying to find the thing which minimizes the sum of squares of errors, right? But what I'm saying is if you're using the minimax, there's just one solution. Now, no exact solution exists for more than three views. David Nister came up with a way for solving it for three views, which involves the solution of a polynomial of degree 43. And if you go to three views, etc., the degree of the polynomial goes up cubically. So if you're trying to do 10 views, it's probably, I don't know, a polynomial of degree 1,000, which you have to solve, and that's just virtually not on, really. So, but under L infinity norm, you can solve it, because each of the basic reason is each of the residual functions is a quasi-convex function, and it's solved by second-order cone programming. Right, so triangulation, that's the problem, and as before, you solve it by this process of taking smaller and smaller cones, and well, until you find the cones which just intersect in a single point. Second problem, partial structure and motion. It says, assume calibrated cameras. Now I'm going to assume that rotations are known. Now, later, I'm going to show a large part of my talk is how to deal with rotations, right? Now, assume rotations are known. So supposing from some process I've worked out what the rotation of cameras are. So here's the problem. I've taken a camera and I've moved around and I've got points in view in each. I've done correspondences. Say this point in this image is where this point in this image is the same as this one, etc., etc. A bunch of correspondences. Now, what is the motion of the camera and where are the points? This is the problem I'm basically trying to solve. Reconstruct the world, reconstruct the camera trajectory. Now, I'm assuming in this problem I know the rotation. And there are processes by which you can find the rotation. It turns out that so what you have is you're given points xij in several views. This is the ith point seen in the jth image. You don't have to know them all. Find the positions of the points and the cameras that minimize the projection error. So here is the problem. Schematically, if these represent, the blue circles represent cameras, the black circles represent points, all you know is that point is somewhere in that direction from the camera. You don't know the distance, but you know think of these as unit vector. You know the unit direction from there to various ones of the points. The question is, where are all the points and where are all the cameras? Now this is a problem that if you try and solve it in L2 norm, it's difficult. There are multiple local minima. In L infinity norm or minimax, there's only one solution. Homographies, given a mapping from points in one plane to a points in another plane or an image, you can solve exactly what the optimal homography is using this general technique. Structure from motion using a reference plane. Given reference plane, this is work similar to, if you're familiar with it, Carlson and Rother. People in Microsoft seem to come up all over the place in this. Carlson, Rother, David Nister, right? In any case, that's the nature of the field, I guess. So if you have a reference plane where you've managed to find match points on a single plane, right? You found a plane in the image. Might be just the ground plane, or maybe the face of a building. If you can align those by homographies, and a homography they will be associated by a homography. That's the sort of a planar, simple planar mapping. Then you can do the complete reconstruction in an optimal manner in this L infinity norm using this technique. The mathematics all comes down basically to the same sort of thing. Stitching partial reconstructions, work I did with a student of mine, CVPR last year. Was it only last year? Using image pairs or triples, you estimate rotations between images and then sort of reconcile them. So you're doing partial reconstructions. You're taking them in lots of 3 and doing a reconstruction from 3 images at a time. Now reconcile them so that you get the whole thing for all the images at once. That can be done using this technique. Other problems. Camera resection. In other words, where is the camera given images from the world to the image? You can work that out in an optimal fashion using these sort of techniques. Projections from PN to PM. Minimax vanishing point estimation. Finding line. If you find vanishing points in an image, given lines can be found in this method. Estimation of uncertainty. You got uncertainty in your measurements given by Gaussian uncertainty ellipses. Can be solved. Projective triangulation, projective structure from motion given plane correspondences. The difference in that is projective rather than Euclidean. So all those belong to past literature over the last few years, and they're solvable. Yes?
So for triangulation, it was a second-order cone programming that you used as the computational technique. Then
yes.
Is there a common underlying computational engine that is used in all these?
Second-order cone programming in all of them.
All the same?
Yes, it's all second-order cone programming. They're all sort of almost identical problems, really, in what's important, the important aspects of them. The cost functions are always image point measurements. And so the cost functions are always sort of similar in their form, right? So it's all second-order cone programming. Now, there are, no, I won't say anything about that at this point. But here's the issue. how do you incorporate rotations into this methodology? In all the problems that I've mentioned, I've assumed you've known rotations or something or other, or rotations were not an issue, right? But rotations are where this whole thing starts getting a bit difficult. If you start having rotations, you no longer have the same properties.
Richard?
Yes?
I guess you're also assuming that you also rejected all the outliers.
Yes, well, I didn't. I just this morning took out the slides about outliers, but we did have a paper last year as well with the student Christy Sim where we give an approach for getting rid of outliers. Outliers are, in any of the experience, really don't seem to be a problem. I mean, you use standard techniques for getting outliers, like ransack, first of all, and then solve the problem. Or you can actually, as I said in this paper from CVPR, use this technique itself in a principled way to get rid of outliers, and that seems to work quite well. Okay, but it doesn't really seem to be an issue. The results that you get are good. All right, but in any case, what about rotations? Once again, just give me a chance to catch my breath. So Hardy said, sort of mathematics is useful to a superior engineer or a moderate physicist. There's no aesthetic value. There's no interest to the real mathematician. Well, I can poke fun at this now because I sort of count myself on the engineering side, right? But it's clear where Hardy's prejudices lay. Just by the way, there's a thing called Hardy's inequality, which I presume has significant aesthetic value and is of interest to the real mathematician. But I think that the real Hardy's inequality is this one, right? So, all right, essential matrix estimation. Now, once upon a time I swore I would never write another paper on estimating the essential matrix. There are so many papers on estimating the essential matrix, I didn't want to see another one. But then I found that you can actually find an optimal solution. So I thought, why not write the paper which will stop anyone from writing any more papers on the essential matrix, because you come up with the optimal solution. I should say, unfortunately, I'll still get people like Singbing who said, well, yes, but this is L infinity. It's optimal for L infinity. And still, maybe that's not a good thing. Well, I will be talking about L2 a bit later on. So what is the essential matrix? It's been around since 1982 or so, when Longet-Higgins came up with it. It encodes the relative displacement between two cameras. So you've just got two images with a calibrated camera, and you want to know what the rotation of the camera is and what its translation, right? Just from point correspondences between the two images. And so let's think of it just in terms of the problem of take two images with a camera and get point correspondences, then compute the rotation and the translation the camera has undergone. And I'm not actually going to even write down, I don't think, the definition of the essential matrix. But I'm going to say here's the way this is done. If we knew the rotation, we could find the optimal translation. You may have missed, but that is the problem, the second problem I talked about. If you know the rotation, take two images of a set of points, you can then work out the translation of the camera, and you can work out where all the points are, in fact, as well. You can even do it for n cameras, n views, but for two it's easy. So here's the algorithm. Do an exhaustive search over all rotations and find the best solution. And the one which gives the best, then find the translation, find the one which gives the smallest error, and that's your solution. Okay. Now, that's very well, but of course there are an infinite number of rotations, so you want to do that without considering an infinite number of rotations, right? But we really want to be guaranteed that we know the solution. So it's not enough to just randomly sample and hope that somehow you haven't missed it. That's not good enough for me. So here's the general idea. This is supposed to be rotation space. And here, now rotation space is actually a three-dimensional space, as we'll see. Parameter is a three-dimensional manifold known as SO3. But I draw it in two dimensions, and I'm supposing here's a point in rotation space. So that point represents a given rotation of the camera, right? I say, all right, suppose that is the rotation, and then I try to estimate the error. right? What is the maximum error for the best translation? The minimum error, rather, for the best translation. And supposing that is 0.1, whatever it might be, let's say radians or degrees. The errors can be considered in degrees, which is the distance between where I think the point is and where my model would say the point is, right? So that's a degree. This is measured in degrees, the error, or radians. Now, so I say, well, what about this rotation out here, right? What about this one? So you then look at that and you find, well, this has an error of 0.4 degrees. So the question is, this one is clearly not as good as this one. This is a better solution, right? Not as good. But the point is you can say more than that. You can say for all rotations within 0.3 degrees of that, you cannot do as well. There's a little bit of, it's a fairly simple thing. But basically, if I take the camera over here, and that gives you a solution, I change it by, 0.3 of a degree, the point projections are going to decrease by at most 0.3 of a degree, right? The errors. So I can say that within some radius about this estimated rotation, I cannot do. So not only can I eliminate that rotation, I can eliminate all rotations around it, right? So that's the idea. And that's going to allow us to do this without having to try infinitely many rotations. So let's just look at some of the details of that. Quaternions. Quaternions give you a good representation of rotations. For those who haven't come across them before, a quaternion is a 4-vector, real numbers, and every rotation is represented by a unit quaternion, in other words, a unit length vector. And the way that works is, if you write it as cos theta on 2 and sine theta on 2 times some unit vector, it turns out that will be a unit vector, a 4-vector, 1 unit there, 3 components here, it's a 4-vector. Then this represents a rotation through angle theta about v. Don't know why I've written a there. About the axis v. So that's the geometric interpretation. So here's v. You rotate about an axis. That'll be represented by a quaternion of that form, where theta is the angle that you rotate. And the interesting thing is that q and minus q represent the same rotation here. That's the way it works. So, in a sense, the quaternions can be thought of as points on a unit ball, points on a unit sphere, rather, in 4 space, where there's a 2-to-1 mapping from quaternions to rotations. And this preserves multiplication in that if Q1, one quaternion, corresponds to some rotation, Q2 corresponds to some other rotation, you multiply quaternions by a multiplication which I haven't actually defined, but there's a multiplication defined on these, and that actually corresponds to the product of the 2 rotations. So this is an isomorphism between unit quaternions and rotations. Actually, it's a 2-to-1 mapping. Now, the interesting thing, which is not so often pointed out, that's sort of standard, but what's not so often pointed out is that not only that, it's an isometry. So what that means is that, this is supposed to represent the unit 4 sphere. 2 quaternions, there's a distance on that sphere between these 2 quaternions. That distance is equal to the angle between that distance is actually the same as the angle between the quaternions, or the cosine of the angle, or something like that. But the angle between the 2 quaternions is half the angle between the corresponding rotations. So what's the difference between what's the distance between 2 rotations? It's defined by, take one rotation, another one. What is the distance on my rotation space? Well, that is I define to be the angle between the angle of the rotation R1, R2 minus 1, right? So 2 rotations are close if you get one from one to the other by just a small rotation. And that is also, so that distance is equal to the distance on the quaternion sphere with a factor of 2 in there. So that's a good representation of rotations. So all rotations within the delta neighborhood of a reference rotation form a circle on this quaternion sphere. Okay, now remember, see what I'm trying to do is I'm trying to say, here's a rotation, I've got an error for it, therefore I can eliminate all rotations on that ball, on that circle around this one. So, now, working in quaternions. Now the only trouble here is I now want to be able to sample this in some reasonable way by little balls that cover it. It's a lot easier if I do this in Euclidean space. So what I'm going to do is cut this in half because it's a 2-to-1 mapping and I really need the top half, and flatten it down like if you took a tennis ball, cut it in half and pushed it flat, right? And so that is what's known as, you get what's known as the angle axis representations. You flatten out meridians. So if I take this as rotations, I flatten down. This is what happens if you take the map of the Earth. You get what's known as the azimuthal equidistant projection, where distances along lines of latitude are the same, and you stretch slightly tangentially. So I do this with the quaternion sphere, and I flatten it down onto what's now 3 space. It's 3-dimensional space. So this is just a thing called the Tissot indicatrix. It shows the distortion that happens when you do this. These sort of distortion ellipses, you think these are sort of like what happens to an infinitesimal circle. It gets stretched. But you only have to go out to the equator because you're only using, it's a 2-to-1 mapping, you only use the top half of the sphere. Very little distortion really occurs out to the equator. So this is a fairly distortion-free mapping, which we can now use to represent rotation. So, okay, the underlying map is nothing. It's just an what did I say they were? Azimuthal projection of the Earth, just to give the idea. And now, I have this thing in now 3-dimensional space. I can only draw it in 2, which is now a representation of all rotation space. So here's the idea. I say, okay, let's try this rotation here. And I say, and I estimate using my technique, second-order cone paradigm, what the maximum error or the minimum error is. And I find that if that's the error, I can rule out this whole square because I can actually rule out the whole sphere. So that means, okay, I'm done with that. Then I go on to the next one. And I find I can eliminate that whole region of rotation space all at once. Then I go to this one, and I find, unfortunately, that this circle, maybe I should have drawn that different, this circle doesn't cover the whole thing. So what I do is I subdivide that. I subdivide that section, and I can now look at them. I can eliminate them one by one. This is this technique known as branch and bound. So I'm just sampling, running over the whole of rotation space, eliminating what I can according to that criterion that I've sort of started with. And if I can't, I subdivide and then see if I can eliminate the smaller things. Yes?
So in the first slide, which you had 0.1 and then 0.4, which allowed you to say 0.3.
Yes.
But here there was no 0.1 to start with, right?
I have to start with an initial solution.
Okay.
I have to start with an initial solution. It doesn't matter how good that solution is really. It can be anything, but I use a standard algorithm to compute. And that gives me an initial error. I know that there is a solution which has such and such an error, right? And then my next point, I choose to be here, and this is the circle, which is the difference between the errors, radius, which is the difference between the errors of the best that I have and the error here.
So the first point you choose is kind of crucial because you determine how fast you can...
Well, yes, but as you go, you get better points, right?
Okay.
I mean, the point is, what you actually do here, if you don't succeed, let's see, how's it? Yeah, if you don't succeed, then if the thing is small, that means there's the possibility that there's a better solution inside there. So you take the center of the box and try that one and see if that is a better solution than the one you have. And if so, you discard it and keep going. And you'll find that if you do this in a sort of a breadth-first manner, in other words, try low resolution first and then keep going, you keep getting better solutions as you go along. So it's not too critical, but not too critical. Right. Now let's see what happens. Ultimately, you're looking at lots and lots of cubes along the way. And as you go, as I said, you start at a given subdivide into cubes of a certain size, and you do all them, and then you subdivide into small. Each of those I call an iteration every time I go down one level. And I go down to 11 levels of iteration in this. So ultimately my cubes are very small, and what's left is very small. And here's the number of cubes which I actually consider at each level. And this can go up to about, this is 10 to the 6th, up to, in some cases, up to close to 1 million cubes I have to consider at a given level. So you've got to do this fast, right? You've got to do it fast. And ultimately, though, it starts decreasing. This is a graph of the remaining area of volume of rotation space that you know the best solution must lie in. And ultimately, we're down to 10 to the minus 5th or 10 to the minus 6th cubic radians after so many iterations. So that's the algorithm effectively. Now, one of the things that you can do with this, which you didn't know any way of ever doing that, compute the essential matrix from 3 points or 4. Now, typically you need 5 points to compute the essential matrix, right? If you use 3 points, you can get something. You don't get a single estimate of the rotation, but you get the rotations actually form a surface. There's a surface of possible rotations, which are compatible with 3-point correspondence. Or with 4-point correspondences, you get a bunch of lines. They're thickened here a bit, but essentially they're lines. Not straight lines in rotation space, they're just lines, one-dimensional manifold. So you can do that. Now, I did say you have to do this very fast, right? You have to do this fast because you can be looking at 1 million cubes. So I had to think of a quick way of doing this. Second-order cone programming can be a bit slow, right? So let's see what you can do to speed this up. Supposing you've got point correspondences, a point X, which you see in 2 views. And here's the baseline. Here's one camera, then the other. You translate this so you put all these 3 vectors, t, v, and v prime, all at the same point, and it looks like this. Now you say, okay, v and v prime are not exact measurements. There's a certain possible error on these, which is represented by these circles, and the true value of v is somewhere inside that cone. Question is, where is t, the translation? It must lie, with exact measurements, coplanar with v and v prime. See, these are coplanar vectors, coplanarity condition. Now, if these are circles, it must mean that t must lie in this section of space which is bounded by circles, great circles, which are tangent to those 2 circles like that. I hope that sort of get the idea what that's doing. Looked at, this is supposed to be, look at that, the 2 cat's eyes, look at it like that. You can see that t has to lie in one of those wedge-shaped regions. In fact, it really looks like this. The translation must lie between 2 planes, which are the 2 planes of these great circles, in fact. So instead of second-order cone programming, we find that t is constrained by 2 linear inequalities. It must lie this side of that plane and the other side of the other plane. So there's just 2 linear inequalities on the position of t. So then that means that all I have to do is sort of look at, so take a supposed error. What is the best error that I can, well, I won't go into the details of that. I say let there be a certain error, then t must be in this region, bounded by a whole bunch of things, 2 planes for every point correspondence, and then we can see if there is a solution, and that will tell us that there is a solution with that given error. So where this compares with linear programming or second-order cone programming, supposing you've got 100 point correspondences in 2 views, you want to compute the essential matrix. With second-order cone programming, this would be 200 second-order cone constraints in 602 variables, because you've got to estimate the positions of the points and the 2 cameras in the way the standard problem was set up. Whereas with linear programming, you've got 200 LP constraints in only 2 variables, which are the points where that vector meets a plane out here, right? So if LP and SOCP are sort of cubic in the size of the problem, this means that LP will run 5,000 times faster on a problem. of this size. That's even assuming that you could do second-order cone programming as fast as you can do linear programming, which clearly you can't, so that's an underestimate. Sometimes you want to even do this with 1,000-point correspondences, in which case you're waiting weeks to do it with second-order cone programming. No time at all. But okay, let's take some time examples. Notre Dame set, which if you've heard Noah speak, which probably most of you have, you've seen this data set here. With how fast is this algorithm? 29 correspondences, we can compute the essential matrix in 56 seconds on some arbitrarily chosen problem from this. When I went up to 6,000 correspondences, which one pair of images actually had 6,000 correspondences, took an hour and 33 minutes. Now, okay, that's a bit slow, but it can be used as a reference, since it gives the optimal solution. It's one argument. It can be speeded up by orders of magnitude using a graphics processor and using some sort of, this is my speculation, because this is highly parallelizable. Highly parallelizable. You know, you're looking at one cube after the other. So obvious speed up. But the best thing is it works much faster if you use wide field of view cameras. So take the Ladybug data. I took some data with Ladybug camera, which I have. Yes?
Is the number of points that relevant? You're still solving a minimax problem, right? So,
yes.
I mean, any outliers are going to determine the solution.
Well, no, I mean...
You always want to run these algorithms on minimal sets of correspondence.
No, you shouldn't really. I mean, you should really take all your data into account. I mean, you don't know where the best data is. I mean, I took it, you know, people keep coming up with outliers. You know, I took data from Noah's set. There are no outliers in there which cause the solution to be, you know, no significant outliers.
Was that already optimized and all the outliers thrown out?
Well, sure. I mean, we're assuming you've run RANSAC on this, right? I mean, you don't take raw data. Of course you don't.
It was bundle adjusted as well, right? With all the outliers thrown out. There was
Well, whatever. You've got rid of the outliers somehow or other. But I think there are other ways of getting rid of the outliers other than doing bundle adjustment. RANSAC will do a pretty good job on getting rid of your outliers for you, right? And if not, then, you know, I mean, why are you all so skeptical about it? Everyone brings up outliers. I mean,
there's a distribution though,
because,
these
you know,
point matches, right? It's not as if there's inliers and outliers.
Yes.
There's a distribution of error. So it's just that if you use a minimax solution, then you focus on those which are the best.
Yeah, okay. Well, if you don't like that, you use my algorithm for getting rid of outliers, right? I mean, there really are ways of getting rid of outliers. We run this on real data, right? I mean, okay, there are some outliers, and you know, there are a few outliers in Noah's data. We get rid of them, right? You just, it's really not so hard. It really isn't.
I guess my problem is I don't think it's as simple as saying there's inliers and outliers. There's a distribution of errors.
Well, of course there is. There's no such, you know, unique definition of what an inlier or an outlier is. Agreed. Yeah, agreed. But it really doesn't. We run on dinosaur data. We run these things on this sort of data. We run on a bunch of other data. You know, outliers really don't worry you. You know, you get a better quality solution than you risk running an L2 algorithm and getting into local minima and things. Right? Another thing I was saying with this one though, what is the result here? With Ladybug data, with say 2,500 point correspondence in two views, we're running in about 7 seconds. 500, we're running in about 3 seconds without any, you know, anything other than just putting the optimization flag on. So it really does work relatively fast if you've got 360-degree data. If you wanted to parallelize this, which I'm going to try at some point, I believe you can get this down to real time on, you know, 500 images. So. Also works, this is a bit of an extension, it works well for rigidly placed multi-camera systems such as this. This is Mark Polify's vehicle, I believe. Cameras on either side of the thing looking in opposite directions. A slight extension of this algorithm will work well for computing the essential matrix of the rotation and translation of that vehicle. Well, that's somewhat speculative since I haven't actually done it. I'm in the middle of doing that, but there's no real difference between that and a multi-directional camera. Further application, 1D camera. This is some work with Fredrik, Carl, Kalle Ostrom, and 2 other students from Sweden. The idea, there's some work being done previously with, on planar motion. We have a robot which goes around on a plane with a camera fixed in its relationship to the robot, to the plane. And you want to solve the complete structure and motion problem for that. No solution existed, right, other than sort of iterative ones and initialization, iteration. But basically the same idea of searching rotation space works here. So here's an example where they call the hockey rink data, where you've got a thing running around in the hockey rink observing 14 points. And it turns out you can dualize this problem, this thing called Cremona duality or Carlson duality, where you exchange. There's no real difference between points and images here. So you can think of this, turns out, if you take just four of the points, you can look at it as 3 points, or no, 3 views of 37 points, and actually then compute the trace of the robot like that. This will be the optimal solution in L infinity for this. Okay, pause my breath once again. Hardy said, I've never done anything useful. No discovery of mine made was likely to make directly or indirectly, for good or ill, the least difference to the amenity of the world. So I admire his honesty, and I guess were it not for the fact that I had to earn a living, I'd like to be able to take the same attitude sometimes, I think. Then I wouldn't have to worry about outliers. Right. So I see I'm running a bit short on time. I'll just go a little bit quickly on this. Okay. This is a nod to those people who say, well, yeah, L2 is much better. I don't believe it for a start. L2 is equally subject to outliers as L infinity is. You get outliers in an L2 problem, it'll kill you, right? So, however, supposing we want to solve and find L2, one thing you can do is you can use an L infinity solution to constrain the L2, and I don't just mean we're going to use an L infinity and then iterate to the L2 solution from there. I'm going to do something a bit different. The general principle is that a good approximative solution to a quasi-convex problem constrains the location of the optimum in a very distinct way. Suppose, and this can be any solution, it doesn't have to be the L infinity solution, any solution can use is a good approximation. So what it is, if you have the cost, the L2 cost, in these brackets, one day I'll fix this, these brackets should be inside the summation sign. This is the L2, sum of squared cost function. This is the cost, and supposing it's less than epsilon squared. That means that each fi squared is less than epsilon squared. The sum of them is less than epsilon squared, each one must be. And so fi must be less than epsilon for all I. In other words, the residual must be less than epsilon, less than the square root of the L2. So that means that the point you're looking for must lie inside the sets with residual epsilon, which we've seen in the triangulation problem are cones. So this says this optimal solution must lie in these intersection of cones. I can compute those cones and say, here's a region of space, and the optimal solution lies inside there. So my strategy is find a good approximate solution, evaluate the cost, then find this solution, find this region, and then try and show that in that region your cost function, the squared cost function, sum of squares cost function, is convex. Right? I'm going to try and show that if we can show the error function is convex on that restricted domain, I must be able then to know that I can go directly using convex programming to the best solution. So how can you know that it's convex? Well, let's have a look at some elementary calculus. For one-dimensional functions, a differential function has a stationary point when its derivative is 0, right? Everyone knows that, right? And if the second derivative is greater than 0, it's a minimum. If it's less than 0, it's a maximum. Otherwise, it may be a point of inflection. So there's the standard picture, right? So now what about multidimensional functions? A function has a stationary point when its Jacobian is 0, sort of like that. The plane Well, Jacobian is 0. And here's the important fact. The Hessian of the function is a matrix of second derivatives. If that is positive definite, then the function is convex at that point, right? So that means if you can diagonalize the Hessian by orthogonal change of coordinates, the diagonals are the eigenvalues. If the eigenvalues are positive, the Hessian is positive definite, and f is convex. If they're negative, it's concave, and if they're mixed, then you have a saddle. So Hessian positive definite, it's convex, and it's a minimum point. Hessian negative, it's concave, and you have a maximum. Hessian mixed has negative curvature, and it's a saddle point. So what we want to show is that the first case applies in this domain that we know the solution, the best solution must lie in. So how do you show that it's positive definite? You look at the Hessian. So supposing the camera is just this simple, we arrange our coordinates so that we're looking straight down the z-axis towards the point. The cost is Euclidean distance, and the Hessian, remember this, so I'm looking at L2 problem here. The Hessian is this. This is the form of the Hessian. You can compute it. And the trouble is, this has 2 positive eigenvalues and 1 negative eigenvalue. And that's why, it's another way why this problem doesn't work well. If this were 3 positive eigenvalues, no problem. But a negative eigenvalue is sort of aligned close to along the z-axis. Now here's the real trick. You can get a uniform diagonal bound for the Hessian to show the Hessian is greater than in the positive definite sense this thing here, where this is epsilon is the maximum error. It's the difference between the projected error and the axis. And the proof is you just subtract them and look at the eigenvalues, and that's what they are. Now the Hessian is the sum of Hessians. So if I got several measurements, I compute the Hessian for each one, and I sum them, and that's the Hessian for the total error. Now, without going into the details, because we're sort of short on time, if I write g is the distance of the point from the camera, and the depth from the camera, and u is the direction of the ray from the camera to the point, then it turns out that the cost function is convex if this condition holds. And A is defined in some way, doesn't matter. We won't go into the details. This is the definition of A in terms of the depth and the vectors to the points. And it comes up, so you can get these little conditions which actually fairly simply expressed involving the maximum and the minimum depth of my region from the cameras. Easy things to compute. Test this condition, either one of these 2 conditions. Don't need to look at them. And if that is a positive definite matrix, then my region is convex. Has 2 large positive eigenvalues, 1 negative one. The Hessian of many cameras is the sum of the individual Hessians. If the view directions are not close to parallel, the point is, really behind this, is the positive eigenvalues for one thing overpower the small negative eigenvalues for the other measurements. And so the total thing turns out to be positive definite. So for the case where the view directions are near parallel, you have problems, and there's another trick you can apply. But if they're not, typically the test will work. Gives you a simple test, takes about 1 millisecond to try on any given example. And here's the results. Once again, on the Notre Dame set, 277,000 3D points are triangulated here, and I tried each of them. All but 281 were proved to be optimal, or proved that it was convex in that region by this test, and by the second test, which is slightly more sophisticated, all but 153. So less than 0.1% of the points failed this test. The others, so we have a test here which worked in 99.95% of cases to actually prove optimality of the solution. So you're able to test very quickly and prove that you've got the optimal solution in these. So that's it basically fails when the camera rays are almost parallel. There's another trick you can apply then, which I have not actually programmed to see how it works. But so, final thing, I'll stop here because of time. Pure mathematics, I think this is a useful one, actually. Pure mathematics is on the whole distinctly more useful than applied. Right? What is useful above all is technique, and mathematical technique is taught mainly through pure mathematics. I believe it. I'm going to skip over that and stop with a final one. Young men should prove theorem, old men should write books. So I'm devoting myself to books for now. Right. Let's see.
Any other questions for Richard?
Yes.
So I might have missed this, but going back to the solving the essential matrix by sampling the rotations.
Yes.
So when you go to the general structure motion problem, you have n rotations to solve for.
Yes.
So how do you sample in that space?
I'm not claiming that you will be able to solve it. I mean, in principle, yes, you can use it. Unfortunately, you haven't got time. Unfortunately, you're then sampling in a 9-dimensional space, and every time you subdivide, you're getting 2 to the 9th. You just don't have time to do it.
I thought maybe you talked about the dual, so I thought maybe that was.
Well, the dual, to use the dual thing, you've either got to have a small number of cameras or a small number of points, right?
Right.
Otherwise, then you can dualize it so you have a small number of cameras, right? Then it'll work. Otherwise, no. I mean, in principle, this would give you an algorithm which would solve general structure and motion, and you can't. No, you can't do it really. So that's why the case with the vehicle with several cameras, you can, because there's still only one translation and one rotation involved. And so you're still only sampling in the 3-dimensional space, and so you have time to do it. Right. Yes?
So if you go down to 10 to the minus 9, is there a technique to figure out what is the actual rotation in that little volume?
Well, only within a given, within any given bound, right? I mean, if you wanted to get it more, 3 more figures of accuracy, just iterate a little bit further, right? But no, you have to stop somewhere.
Right.
Just as there's always a stopping criterion for.
So there's nothing like a continuous minimization that you can apply in that little volume, or I guess it's always iterative, right?
Yes, they're always iterative, right? So, and any iterative technique, you sort of stop when you think you're close enough for your purposes, and that's the same here, really. But no, I suppose, is the answer. Even if you think that convex iteration can get you to a perfect solution, I don't have any way of doing that.
So that's a positive no, meaning saying there's definitely not a technique that will ever do it. I mean,
well. We're dealing with computers here, right? And computers only have finite accuracy, so in that sense, you can't ever ask for anything better than that. And given that there will not be a closed form solution that you can...
Right, that you're saying positively there's no closed form solution at one point.
Oh, pretty positively, there's no closed form solution that you can ever use to this. No, you're only going to be able to get as accurate as you ever want to get by computing long enough. And, get 3 more every... it's linear convergence in a sense. Every extra digit gives you an extra equal amount of time to compute. But I've computed 6 decimal places or so. If you want to go to 12, it'll take twice as long. Right?
So this technique may not work, but once the perturbations to rotation matrix are small enough, right, they can be approximated by a linear matrix, a matrix linear in the infinitesimal rotation.
Well, okay, that works. I should have said we can also do this in the pose problem, camera pose. Given 3D points which you know and a camera that you know, then you can compute the pose. There's no, in L2 norm, once again, this is one of these problems. There's no real solution guaranteed, but you can use this. technique. And in that particular technique, but not in the essential matrix, you can, instead of taking effectively what I'm taking is a 0th order approximation of rotation, you take a first order approximation using Rodriguez formula, or the truncate after length, then you can do it, and it will, instead of, in these things, you have this thing as less than epsilon, I can put that as epsilon squared in that particular case. It means you're going to be able to converge much more fast. But to the best of my ability, I could not see how you do that in the essential matrix. There are reasons why it can't quite work very technically. Looking into it, it doesn't work for the essential matrix, taking the first order approximation of the rotation. No, I looked at that for quite a bit, actually, because it would speed things up substantially. Yeah.
Any other questions? Well, if not, let's thank Richard again for his talk.